Okay, in this podcast we're going to talk about acids and bases, and this is the first podcast where we're going to talk just about introductory stuff. Okay, so as you know, there's lots of definitions about different definitions of acids and bases. The earliest definition was the Arrhenius definition, named after a scientist named, surprise, surprise, Arrhenius. And he said that an acid is a substance that, once dissolved in water, increases the concentration of hydrogen ions. Hydrogen ions being H+, right? And a base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. Okay, now this definition didn't quite work satisfactorily, because it was noticed that a lot of substances that did not have produced hydroxides or did not have hydroxides also had properties of bases. So along came both Bronsted and Lowry, who at the same time came up with a similar definition, and they weren't working together, but because it was happening at the same time, they gave them both credit with their name. So Bronsted-Lowry says that an acid is a proton donor. Now a proton is also an H+, because if you think about it, a hydrogen has one proton, right, by definition, and it has a mass, the most common isotope has a mass of 1.0 mass number, and so that means it has one proton and 0 neutrons, and because it's neutral, it also has one electron. So if it loses that, hydrogen loses that electron, it becomes H+. And therefore, the only thing left, there's no neutron, there's no electron, the only thing left is a proton, which is why we call this a proton. Okay, so an acid, according to Bronsted and Lowry, donates a proton, and a base accepts a proton. Okay. So in order for a substance to be a Bronsted-Lowry acid, it must have a removable proton. Okay, and boy, I'm talking about acids and bus. A Bronsted-Lowry base must have a pair of non-bonding electrons, lone pair. If it can be either an acid or a base, accepting and donating, it's known as amphiprotic, which means it can donate or accept a proton. And we call a substance amphoteric if it can act as either an acid or a base. So amphiprotic or amphoteric. So the most common substance we talk about as being amphoteric is water. It can act as both an acid and a base, but also this hydrogen carbonate or hydrogen sulfate ion can also be amphoteric. So let's talk about what happens when an acid dissolves in water. So if I take hydrochloric acid and put it in water, what happens is the water attracts this hydrogen ion, and it becomes this hydronium ion, H3O+, and we're left with the chloride ion. Okay, so water in this case is acting as a base, right? It's accepting a proton, and as a result, we end up with an acid. This is now available. This hydronium ion has an extra H+, and it's available to donate it. So we call this conjugate pairs. Okay, so the water originally acts as a base, and once it accepts the H+, it is now the conjugate acid. Okay? Alright, so water can act as both an acid and a base. In this case, it's acting as a base. So the term conjugate comes from Latin meaning conjugare, or joined together. like conjoined twins, right? Alright, so if I have here I have nitrous acid, and if it loses the H plus from here, whatever it becomes is now the conjugate base. Okay? So here it becomes a conjugate base because now it is available to accept, if it's going this way, it's available to accept that H plus. Okay? And water acting as a base here means it's available to accept an H plus, which it does from the acid, and becomes H3O plus. So an acid minus one H plus becomes a conjugate base, and a base plus one H plus becomes a conjugate acid. So reactions between acids and bases always yield the conjugate acids and bases. So let's identify. Alright, so let's take a look. What's the conjugate base of each of the following? Okay, so the conjugate base means that it's lost the H plus. So what I need to do here, in all cases, is I'm removing an H. Where's my pen? I'm losing an H and a plus, right? So if I lose the H, I become ClO4. If I lose a plus, it becomes minus. H2S is going to lose an H, just one H, to become HS, and it's going to become minus. pH4 is going to lose one H, so it's going to become pH3, and it loses the plus and becomes neutral. And HCO3 minus loses an H to become CO3. It already had a minus 1, it loses 1, becomes a minus 2. Alright, so the conjugate acid of each of these is going to be whatever this is plus an H and plus a plus, right? So this becomes HCN, it gains a plus, so this becomes neutral. HSO4 becomes SO4 2 minus adds an H, just one H, becomes HSO4, because it adds a plus, it becomes negative 2 plus 1 or minus 1. Okay? H2O gains an H, so it becomes H3O and a plus. HCO3 gains an H, so it becomes H2CO3, and it becomes neutral because it goes from negative 1, gains a positive 1, and becomes neutral. Pretty easy. Alright, so here it tells us that the hydrogen sulfite is amphiprotic. So write an equation for the HSO4 with water in which the ion acts as an acid. So let's do that. HSO3 minus plus H2O. So the ion is going to act as an acid, which means it's going to lose an H plus, and that H is going to go to the water, which will become an H3O plus whatever's left, SO3. Now it's lost both the H and a charge, so it's going to become a minus 2. Okay, so write the equation for the reaction of HSO3 minus with water, in which the ion acts as a base. So if it's a base, it is going to accept an H plus, so it's going to become H2SO3, gains an H and a charge, so it becomes a minus 2, plus what's left here once it loses the H plus is the OH minus. As you know from Honors Chem, we have strong and weak acids and bases, and the definition of a strong acid strong means it completely dissociates. So if I start with HCl, let's say this is the amount of HCl. Once I put it in water, I'm going to end up with all H plus and Cl minus, and there will not be any HCl left. There'll be 0 HCl. Okay, so it completely comes apart. There's no HCl left. So there is no two-headed arrow. It becomes H plus plus Cl minus. There is no reverse reaction. Okay? So there are some acids that are strong, and you need to memorize what they are. And these are 3 of them: hydrochloric, sulfuric, and nitric. Now, if you have a strong acid, as it turns out, their bases are very weak. If you have a weak acid, their conjugate base is going to be very strong. Okay? So the conjugates are opposite in terms of whether they're weak or strong. So weak acids only partially dissociate in water. So if I have, let's see, acetic acid, and I put it in water, I end up with H plus, well, the hydronium ion, plus C2H3, the acetate ion. But my arrow is big time to the left. Very little of it comes apart. Most of it stays intact as acetic acid. So if I have if this is weak, a weak acid, the conjugate base of that is going to be strong. So the acetate ion is going to be strong. Okay? Okay, so in any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. Okay, so let's take a look at what that means. So if I have HCl and water, here this is acting as an acid, this is acting as a base, this is acting as an acid, this is acting as a base. So this is going to shift either right or left depending on which of these 2 bases is strongest. Okay, so if I look back at that table and I compared H2O and HCl, H2O is up here, it's negligibly strong, and the Cl is even weaker. So the H2O is the stronger base, so the equilibrium lies far to the right, because equilibrium will favor the reaction that moves the proton to the stronger base. So it's going to favor this happening, this proton going over to here, causing this to happen, okay, this to form. So the equilibrium will shift. It'll be very little or nothing going this way, and because it's going to shift to the right, K, the equilibrium constant, is going to be greater or much greater than 1. Okay, so in any acid-base reaction, the equilibrium will favor the reaction that moves a proton to the stronger base. So again, we have this is acetic acid. This is, and be careful with acetic acid because it gets written different ways. Sometimes it's written as HC2H3O2. Sometimes it's written as HCH3COO. So you got to recognize it all those ways. So this is an acid, this is a base, this is acting as an acid, this is a base. And if I looked at the previous table, this is the acetate ion, and this is water. So it's going to go to the stronger of the two bases. And the stronger of the two bases is going to be the acetate. So it's going to move the proton to this, which causes the reaction to shift left, right? It wants this to form. So because it's going to shift further to the left, K is going to be less than 1. Okay, so let's take a look at another one. Alright, so for the following proton transfer reaction, use 16.4, which is right here, to predict whether the equilibrium lies predominantly to the left or to the right. Okay, so here I have HSO4 minus plus CO3. Let's see what's happening here. So this is acting as a base because it's picking up a proton, right? And this is acting as an acid because it donates the proton. Okay, so this becomes the base. So I have two bases here. I have CO3 minus 2, which is right here, and I have SO4 minus 2. So the stronger of the two bases is right here. So the proton is going to move over to this base, shifting the reaction to the right. So the K is going to be greater than 1. Let's take a look at a couple more. Alright, so here I have HPO4, and it is acting as a base because it's accepting the proton. So here it's the base, here it's the acid. Water is, in this case, acting as the acid. It has an H plus, which is donating, and this is the base. Okay, so I'm going to compare HPO4, which is right here, to the hydroxide. The hydroxide is stronger, so the hydroxide is going to accept the H plus and shift this way. Okay, so it's going to shift to the left, and K will be less than 1. Here I have ammonium and hydroxide. The ammonia donates a proton, so that's an that's acting as an acid. This is acting as a base. In this case, the ammonia is the base because it's accepting a proton when it goes this way, and the water is the acid. So if I compare hydroxide, which I have right here, and ammonia, which is right here, the stronger of the two is the hydroxide, which means that this H plus is going to come over here to become water, causing a bigger shift to the right. So K is going to be greater than 1, and it's a right shift. Okay, so in the next podcast, there's a Khan Academy podcast where it talks about the auto-ionization of water, which means that water comes apart to form H plus and OH minus at very low concentrations in water, but they do it does ionize on its own, so it's auto-ionization. So he's going to talk about that, and then talk about the relationship to that to pH and pOH.